Hi everyone, this is Vincent Willegragen from his channel Complex Chemistry Explained. And finally here's the first example of a weak base and a weak acid. For some reason this video didn't want to upload, but here it is now. So we have 80 milliliters of ammonia with a concentration of 0.4 and 70 milliliters of acetic acid with a concentration of 0.5. and a Ka value of 1.8 times 2 to minus 5. Negative 5 is given. Calculate the pH value at the end point or the equivalence point of the solution. First step is to write a balanced equation for this. So, then the first step is to calculate the number of moles of both the base and the acid. And the milliliters will be derived to liters, that's why it's 0.08. So it's 0.02 mole. And then the acid. Now we can see that the acid will be in excess. Oh wait, no, I don't want to do in blue, it'll be confusing. Let's do this purple. So this is the amount that will be subtracted, so there will be no ammonia left. No, this is plus on the right side. Okay, so and then we have the excess amount of acetic acid, which will be, you can subtract 0.02 from 0.05. The answer will be 0.003 mole, right, or moles or whatever, it's just an abbreviation. Now we write a second balanced equation with the excess amount of acetic acid, which is in a watery solution. That's why water is to be added. Well, we have to do something with the equilibrium constant here for the acid. That will indicate the pH value or this concentration. Well, what we have here, firstly we need to calculate this concentration. Remember to add the volumes. The total volume will be the sum of those two. And this answer will be, I have my calculator here. Oh no, what did it do? It was 0.03 divided by, I can see it's 0.15, so that value will be 0.02. Okay, we have 0.02. No, another color again, orange. I'm writing the equilibrium concentrations here. This one, see, this is in a different phase. These are all in solutions. See, those are solutions, and this is liquid. So what we do now here now, this one was, I still have to calculate this one too. 0.032 divided by 0.15 plus x, and this one will be x. And this gives us a value of 0.213 plus x. This is a repeating 3. We'll repeat on and on. So the equilibrium constant was given, and we will use that to calculate x. first all the products and reactants that are involved in this equilibrium. Water, however, will not be involved in this. So now we can substitute all the values. You can say that x is a minuscule number, so you just leave those two, you can take them out, but I think we can somehow calculate it without deleting the x from the equation. Then it will be a more precise value. Okay, now we can put x squared in front. It will make it just, it looks just more understandable. Minus, and it will be equal to 0. So now we can, I think we should simplify this. No, you can, no. Okay, so that here is the value 0.2133513 minus is 0. So now we can have a very special setting on the calculator here, equation 3, and A is 1, B is 0.213351. You can just put a few 3's there. And then off to C. C will be minus 3.6 times 10 to negative 7. Okay, X is 1.687344 times 10 to the negative 6, or X is minus, this one is not applicable. You see, it's a negative value, but however, this will be the hydronium concentration. And now finally we will come to the pH value. So it's minus the log of the hydronium ion concentration. So, and now insert that. Okay. Go back to statistics. Minus log 1.687344. I think that is a no. Minus log 1.687344 times 10 to negative 6 gives us a value of 5.77. So here you can see the calculation again. Number of moles of base, number of moles of acid, excess amount, then the second equation with the equilibrium constants, then the calculation and the substitution, then the value of X, and mind that the value of X is the hydronium ion concentration, and then you substitute that in the pH formula, and then you will have the answer. 5.77. I hope you understood this one, and thank you for watching, and see you for example 3.